Hello everyone, this is Mr. Harris with the last video of the Polynomials unit. Expect a test this Friday. I'm not going to attach a quiz to this, but I will be posting a bunch of quizzes you can use as study guides. You do not have to do the quizzes. Treat it as a study guide. The answers will be posted next to the quizzes. Okay, this will be covering graphing in the complex plane, pages 27 through 29, connecting circles to polynomials. Your test will be on pages 1 through 29 of this polynomials unit. The test is this Friday. Pages 30 through 38 I will go through in this video. I'm just not going to test on it, but do review it just for your own knowledge sake. Okay. So let's take this step by step. Complex number exploration. You can read all of these for yourselves. Generally, if you first notice, when we use z is used specifically in this case to indicate that we are dealing with the complex plane. Z is not x, but we treat it in terms of x because I is up here with the y values as well. Okay. So let's just begin. And you will see how the connectedness between polynomials and circles take place. We couldn't really graph this in our calculators because we're just going to be graphing the solutions. And we're going to tie polynomials to circles and angles. Once we see those angle displacements, you will see something that looks somewhat familiar. We've dealt with that in the matrices unit and in the trig part 1 unit. Okay, so looking at this, we're going to have to post the solutions first. So think about what those solutions might be. Think about how we're going to solve it. Generally speaking, if I solve for z squared, I get z squared equals positive 1. Therefore, z equals plus or minus 1 when I take the square root of it. So I have real numbered solutions at 1 and negative 1. And let's think about a circle, 360 degrees divided by 2, 180 degrees. We took a circle and sort of split it into 2, if you think about it that way. So my solutions, 1 and negative 1. The distance, we are connecting the form. Let's just cover the formula for the distance. Formula is very much connected to circles. Make sure I have space. Okay. X squared plus y squared equals r squared. Sometimes people do use z squared as well. Another rendition of that formula is the outright distance formula. If we solve for the distance of any value, root it in this a squared plus b squared equals c squared. Once we take the square root of c, we would have the square root of a squared plus b squared. However, relative to the distance formula, in order to craft it so it's set up so it's the distance between two coordinates, we're going to have to change and alter that a and that b. So in this case, this would be the difference between the x values, and this would be the difference between the y values. Even if we solved it here, let me get my little notepad up. X squared plus y squared equals distance squared. Distance equals square roots. Technically plus or minus, but right now we'll just stick with the positive version of x squared plus y squared. And then for the change in the coordinates, because we have both an x and a y, it's the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And that's the distance formula. Distance formula is very much connected to the magnitude of something. When we talk about vectors, magnitude is the distance from some localized origin point, and the origin point can be placed any which way you want. So that's what I mean, the distance from the origin, 1, 1. The angle, 0 degrees, 180 degrees. The location of the coordinates. I'm not shocked I split a circle in half. State the angle between each of the consecutive pairs of roots, 180 degrees. Symmetric over the x-axis, the y-axis, and the origin. You don't have to know about what it's symmetric over. It's just helpful. Over x, y, and origin. Okay, there you go. Of course, these answers will be posted as well. And this is just for 2 solutions. So when we want to go to a cubic function, this is a difference of a perfect cubed. Again, in the last unit, when we solve functions greater than 2, we had to use various theorems to solve. We had to do that because those were much more complicated functions. It wasn't as nicely laid out. In this case, there is thankfully a formula for the difference in the sum of perfect cubes that will help us out. We're going to use the difference of perfect squares as well. But you'd be shocked the values you would get here. This is just practice using these 2 formulas. Again, make sure you create a cheat sheet. Have these to review. I wouldn't expect you to memorize this, just have it to review. Notice it's a difference, so we have to go this route. First, I'm going to write it as these perfect cubes. So it's x cubed minus 3 cubed is 27. So that's really 3 cubed. So now I know my a is x and my b is 3. So x cubed minus 3 cubed equals x minus 3. I'm just following this pattern, times x squared plus 3x plus 9, or 3 squared. So the good thing is we know one solution is x equals 3, and then we have a quadratic we can solve and get the other solution. 3 times 3 is 9, but 3 plus 3 is 6, so we may end up probably having to use the quadratic equation. We'll get some sort of solution, potentially maybe imaginary, but we know it's a solution nonetheless. Quick sketching, if I know the parent function, x cubed looks something like this. I know it's translated down 27 units. So wherever this is, it will look something like that. And however up I'm going, when x equals positive 3, because we have a factor of x minus 3, let's say this is 3. So something tells me that these 2 solutions will be imaginary solutions because it only hits the x-axis once. It's odd. And we have one solution of multiplicity 1 here. This is multiplicity 2, so we have to have 2 imaginary solutions. So imaginary solutions, I'm thinking, would be somewhere around here, sort of looking like it's pushing the graph down. It's very good to be able to sketch graphs quickly just to get an idea of what it is without all the calculator and stuff. So we're going to definitely use this. I'm even going to keep this off to the side just for reference as we jump to more complicated polynomial equations. And then we're going to be focusing on what do we get for our solutions here and how these roots match up to what we know about the unit circle. So in this case, I have a difference of perfect cubes. This is z cubed minus 1 cubed. I'm going to write it that way. So to write it in factored form so I can solve and get the solutions, it is going to be z minus 1 times z squared plus 1z, or just z, plus 1 squared, which is just 1. So we know so far that one solution is z equals positive 1. I'm going to go ahead and put my real root here. And this is also called de Moivre's theorem. Your book has a very complicated way of addressing de Moivre's theorem. I like this method because it gets to the essence of what's going on. Generally, even throughout college, a lot of colleges, we actually covered de Moivre's theorem in grad school because we applied de Moivre's theorem to, I think that was multivariable algebra, multidimensional algebra, one of those classes. D-E-M-O-I-V-R-E-S theorem. This is in some of the homework, the optional homework. Look it up, compare and contrast. This method is a lot easier. And it only works for perfect cubes, perfect squares, difference in perfect fourths, actually, powers of 4. But it still gives you what you need to know without all of that. So let's continue solving. I'm going to go ahead and use the quadratic equation to solve. I have to sort of do this just to keep track of where things are. Then I could just place it in. Okay. So I have -1/2, 1/2 plus or minus 1 minus 4ac. My brain's jumping around. 2/1. Let me make sure I didn't make careless mistakes. 1 squared minus 4 times a times c. Okay. So we get -1/2 plus or minus the square root of -3/2. From what we know about our unit circle, from what we know about our 30, 60, 90 triangles, 45, 45, 90 triangles, these numbers should already look familiar, even from what we know from our Ayatollah's table. Except in this case, we're dealing it in the frame of mind relative to polynomials. Remember, if you have a negative sign underneath the square root, or really any even root, pull out the I. Just like Kill Bill, pull out the I, pluck out the I, take that out. So it's really -1/2 plus or minus I times square root 3/2. I'm going to have the nerve. You should be doing this on your own. However, I am going to look up the unit circle just to verify. So we can see some of these values in this unit circle. Okay. And as you can see, yeah, you can see this just fine. Square root 2/2, 1/2. Let's find a -1/2, -1/2, -1/2. Square root 3/2, square root 3/2. Remember, if we're on the x-axis, it's a real number. In this case, because it's an imaginary number, I mean, anything that's floating up above you or just drops below the ground can just phase through the ground. Something's imaginary going on, something ghost-like. Keep it in frame like that. Any of these floating up, the y value would be an imaginary term. Only the real numbers are on here. So I'm not shocked we have this and this. So that's where these numbers are. And so let's keep going. And I'm going to go ahead and write these solutions here. And so we had, you don't need the z equals. I probably will stop writing them after a while. But we had z equals -1/2 plus square root 3i, or square root 3/2i. You can even write it like that. And z equals -1/2 minus square root 3/2i. In this case, when we have the I, remember it's x plus y I. This is a complex number. You can even see it as a plus bi. These are complex numbers. This is how we graph it. Here we go to the right, or to the left, sorry, -1/2. And we go up square root 3/2, we go down square root 3/2. But how are we going to know approximately where? Well, imaginary plane, this is 1i. This would be -1i. So remember, square root 3/2, that's like 0.866. So it's about 86.6% of an entire radius, just like we did previously in the year. So we're going to go out to about -1/2. If this is 50%, 75%, for the heck of it, 87%. So I'm going to put a little dot there, or at least an open circle. Because we're working with z, and this is why the notation for z is useful. Because we're working with z, we can sort of fill this in. Because we know this is labeled the imaginary plane, and that's the significance of using that symbology z. Now we're going to go -1/2, 50%, 75%, something like that, and we're going to go here. So the distance between all of these, we could use the distance formula, but we know what's going on here. It's 1/2 is 1 because a circle is a point rotating, a locus point rotating about a centralized point the same distance away. If the distance fluctuated, we would get something like an ellipse. We have one solution at 0 degrees. And even without measuring this, let's take 360 divided by, in this case, we have 3 solutions. 360 divided by 3 is 120. So we're going to break the circle up into 3 sections, 120 degrees apart. So this, and it looks like it would be, and if you actually work out the mathematics, it is in fact 120 degrees. 120 plus 120, this is at 240 degrees. And that's sort of the connectedness between what's going on. The angle between each consecutive pair of roots is 120 degrees, symmetric over the x-axis or the real axis. And this is the cool part of this, the Morse theorem, is you can take polynomials, plot the coordinates by solving, and then see the interconnectedness of circles. Coming full circle, if you will. Forgive me. Okay. So let's move on to number 3. And we're going to factor this because it is a difference of perfect powers of 4. Do see it as z to the 4 minus 1 to the 4th. And also see that we can write this differently. Technically, just like we do for difference of perfect squares, for example, if I have x squared minus 36, I write that as x plus 6 times x minus 6 for difference of perfect squares. In this case, we would be dividing 4 by 2. So that would be z squared plus 1 squared times z squared minus 1 squared. So we really did divide this by 2 because it's a difference. And if you wanted to take the time and you FOIL this out, you would definitely get z to the 4th minus 1 to the 4th, which is just 1. Now remember, this trick only works for the difference of perfect squares or the difference of perfect something's raised to some even exponent, both of them. It won't work for this, but we can solve this and get it somehow, some way. So the next step equals, I'm going to go ahead and address this. This is just z minus 1 times z plus 1. You know we're going to have 2 more solutions because the degree is 4. So let's think about this. Pulling away from this quickly, think about this z plus 1. Z squared plus 1 equals 0. Z squared equals negative 1. Z equals plus or minus square root negative 1. So we're going to say that z equals plus or minus I. If we work backwards further, we could say that z plus and minus I equals 0. So we have our factors, just like we work backwards. If we work backwards here and we had x equals 36, we could say x minus 36 equals 0. So we have z plus I, or 1i, and z minus I. And we factor this completely, and we can easily, again, look and know exactly what the factors are. Isn't that nice? So now let's fill in this table and plot these points. We have 1. I'm going to show you a trick, because generally this was easy enough, we could just plot these. But I'm actually going to put my solutions here, and you'll know why, because it does go counterclockwise starting here. So we have 1. We have negative 1. Let's go ahead and put the negative 1 here. When I solve for this, I get z equals negative 1, or z equals negative I. And up here I get z equals positive I. So I'm just going to label this negative I. So we are starting here at 1, the distance is 1, the angle is 0, going Counterclockwise, as all math goes counterclockwise, our next solution is positive I. Distance is still 1 unit from the origin, radius of 1, but we're at 90 degrees. Then we're going negative 1, still 180 degrees. And then we're going to do negative I, distance still 1, 270 degrees. Again, 360 divided by 4 solutions equals 90, so it broke it up into 90. And those are the values from our unit circle and such. Symmetric over the x-axis, y-axis, and the origin. And the origin. Okay, this is a fun, interesting thing. Once you get the hang of it, it really isn't that bad. You just have to know first, difference of perfect squares, or use that formula for the sum or the difference of perfect cubes. Break it down, get your solutions, plot your points, and then make that connection to a circle, how I'm dividing it by 4, so I'm going 90 degrees. And of course, you know your unit circle. These numbers are all up in the unit circle. That's what it is. Let's jump into number 4 next. Okay. It's getting fun and interesting now. And as long as we can break these down into perfect squares, perfect cubes, we could go on till the cows come home. Do make one notion or notice something. Unit circle, when I solve, my radius is 1. If I wanted to change this, I could change this to 4 or 10. Well, it would be easier. Let me change it to 4. 4 times, let's see what 4 raised to. And that was to the 4th power. So that was 256. Z to the 4th minus 256. I could break that down, take the square root and all that good stuff. And I could work with it this way, 16 and 16. And again, that's how circles are. Circles are the squares. So perfect squares are very helpful in this case, especially when we're thinking about theoretical values. When you get to the real world, you can always plug this into a computer to get all those interesting values, let's just say. Okay, we're going to have degree 6, so we're going to have 6 solutions. Please try to do this on your own. Pause it. That's the way it's done. That's how you do it. You will have a test question on this. And watch your negative signs. One easy way to do multiple choice is if I'm listing all the questions and I just have both of them be plus signs to see, did you actually do this? Are you paying attention? Maybe one question I'll throw out the I sign to make sure you're paying some sort of attention. So I have, this is 1 to the 6. So this whole difference of perfect squares, it's really difference of any even exponent, as long as I could divide by 2 and get a nice clean whole number. So that would be z cubed minus 1, cubed if you will, times z cubed plus 1, cubed if you will. That's why before you do this, make sure it works out evenly, or else you're going to have a bit of a mess on your hands. It's not that it will no longer be in the circle. It's just, it's going to be one of those weird dots that aren't on the unit circle that you would have to figure out using trig or something like that. You can do that. It's just, this is just a theoretical step right now. Difference of perfect cubes, check. Oh, sum of perfect cubes. We could do that as well. Let me look for my little reference point and get my paper out so I can factor this sum and difference of perfect cubes and then list my 6 solutions. Okay. And x, now let's do a cubed plus b cubed equals a plus b, a squared minus ab plus b squared. A cubed minus b cubed, a minus b, a squared plus ab plus b squared. Okay, there we go. Let's do this. So that's z cubed minus 1 cubed equals, just for a point of reference, z minus 1, z squared plus 1z plus 1. 1 times 1 is 1, 1 plus 1 is 2, so I'm probably going to need to use the quadratic equation, and I'm probably going to end up with I. I'm going to leave myself space to do that. I'm just going to go ahead and get the other z cubed plus 1 cubed equals z plus 1, z squared minus 1 plus 1. Okay. And again, I'm writing this just to make sure I don't leave anything out. It's always good to have those little reference points. So we have -1 divided by 2 plus or minus square root of 1 squared is 1 minus, so for A and C, so that's -4 over 2. Looks like we're in another situation where it's -1/2 plus or minus. I'm going to go ahead and jump the gate and do square root 3 over 2i, because we would end up with the square root of -3, pull out that negative sign. Looks familiar. This would be interesting to teach next year with the unit circle, how we divide a circle in so many bits and pieces. Because 360 divided by 6 is going to be broken up into 60-degree units. Okay. We have our two solutions here. We also have our third solution. So we have a solution at +1 and then -1 plus or minus this. So we're going to get, we have z equals -1. And then down here, we're going to have -1. So that's 1/2. Okay. Plus or minus square root of 1 minus. So let's just do 3 over 2i, just to cut to the chase. So it's going to be -1/2 plus or minus that and +1/2 plus or minus that. I'm going to keep this off to the side. Hopefully you have something similar. Keep track of all your stuff. And I'm just going to list my solutions. But as I'm doing that, remember, I'm going to put the coordinates to make sure I'm going counterclockwise. So starting at 1, distance is still 1, angle 0, distance is 1 throughout. If we're going by 60s, let me go ahead and do 60 degrees, 120, 180, 240, 300. Okay. Now my next solution. Starting here, looking at these, it's going to have to be the positives, because we're going to go to the right 1/2 and go up and go down. So this is 1/2. Let's go ahead and do 50, 75, somewhere around 80, 50, 75, somewhere around 80.86.6 or 86.6%. So we're going to have a solution here and a solution here. And I'm going to go ahead and write coordinates for this too, right now, right? 1, 0. This is 1/2, comma, square root 3 over 2. 1/2, comma, negative square root 3 over 2 for that 1/2 plus and minus. Going backward in this direction. So I'm going to go ahead and I'm just going to finish this and then follow up. We're going to have the -1/2 version now. So we're going to have -1/2 plus and minus that value. -1/2, comma, square root 3 over 2. -1/2, comma, negative square root 3 over 2. And then this would be your -1 value, your final solution. 60, breaking it down this way. Going clockwise. So we have 1/2 plus, again, please fast forward these videos if you need. I'm going through all the tedious details. Yep. Square root 3 over 2i, and I'm going counterclockwise in the order in which I have them. Negative 1/2. Okay, 60 degrees between each. Symmetric over the x-axis, y-axis, and origin. Okay, there we go. It's fun and interesting. Now we're going to extend our knowledge a little bit for practice. Solve the following equations graphically, obtain answers in A plus BI form, complex form, using your knowledge of special right triangles. Okay. Simply solving this, I'm going to have z cubed equals -1. And we know we're breaking the circle up into threes. So this will be 1, -1. I'll call this 1, -1. The thing here is, it's a cube root, and I know the cube root of -1 is -1. Mass cube root -1. Yeah. So we definitely have three solutions. If I take the cube root of both sides to solve, I get -1 as a solution. However, we also know 360 divided by 3. We're going to have to divide things. So what I'm thinking we have to do is we have to go back to factoring. Previously, we did this when we had z cubed -1. Now we're going to do this with z cubed +1. So I'm going to go back here and factor this quickly, z cubed +1. So that's z +1, z squared minus z +1. Okay. And I feel like we've solved this already. I'm going to see if I solve this already just to save myself the headache of having to do it all over again. Yep, z squared minus 1 plus 1. We solved it already here, so I'm just going to borrow this answer. It's easy and simple. And that's where we get the three solutions from. So we get z equals -1. In the previous example, when I solve this, I get 1/2 plus or minus square root 3 over 2. So we go out to the right positive. That's why it's still imaginary. Somewhere around here. I'm going to label this just to cover all bases. Negative square root 3 over 2. We have our three solutions. And let's think about what this is and what's going on. It broke the circle up into three sections. We have our three solutions. I'm going to go ahead and write my solution z equals -1, comma 1/2 plus and minus square root 3 over 2i, because we did end up with the imaginary numbers I. It's just set off a little bit different. It broke it up into threes. It's just telling us to start on the negative side. And if you think about it, it's interesting. Previously, it was z cubed -1. When we solve for z cubed, we get +1. And when you jump into polar coordinates, if you ever take a trig college course, making it negative literally means you're flipping it on the other side of this origin. So I'm not shocked instead of starting here, we're starting here because we're starting with the -1. So you can see all kinds of connectedness. And that's what would happen when we simply flip it. It flips over the origin. If this is a coordinate and you want to get the negative version, if this is a coordinate, the negative version, is the same thing backward. And do this as you see fit. I already did the z to the 6. Let me look at, oh yeah, I'm gonna do some of these. Let me do this negative 625 just to show you what it's like doing something where it's not set equal to 1. Let's just think about this, the 4th root of 265. Zoom in. 4th root, math. No, 625. The 4th root is 5. 25. We're gonna have to break it down a little bit, but we're probably gonna break it down based off of, it'll be z squared. Let's do the square root of 625. Get 25. Okay. So I'm gonna solve this way, the same way we solve. Again, this is why you take notes and you look back. I'm gonna solve it pretty much the same way I solved this, except I'm gonna deal with 5 and 25 and all those guys instead of just 1. So let's, there we go. Z squared minus 25, z squared plus 25. So this is going to be z minus 5, z plus 5. We're going to have to break this down a little bit. Z squared equals negative 25. Z equals plus or minus square root negative 25. Z equals plus or minus 5i. Going backwards, z plus 5i, z minus 5i. Z plus 5i, z minus 5i. So this is a factored form. And in this case, our radius is no longer 1, our radius is 5. So we're going to go out to 5, negative 5, because it's the radius of a circle. And z equals positive 5, z equals negative 5 here. And then z plus positive 5i in the imaginary lane, z minus, in this case, it would be z equals negative 5i. So this one would be down here, z equals positive 5i. We still divided the circle into 4s. It's still 90 degrees between each of them. The only thing is you just have to make sure. So 64, I bet you, is a perfect cubed. Yes. Let's just do it this way. I think it's 4. Yeah, 4. So you would be dealing with essentially 4. And I would just factor this the perfect cubed way. Check the answer online. In this case, you realize we started here because when we solve it, it is equal to a positive number. In this case, dividing it by 3, when we solve this, is equal to negative 64. So we're going to start here, but we're still going to have these values here. Do this for your own benefit if you wish. If it's helpful, check the answers. The solutions will definitely be posted. I'm going to leave 2 for you to do on your own. The solutions will be posted online. Look at all these equations for number 2. Lots of equations. But you'll notice even when, I'm going to go ahead and write the equations just because it's interesting for 2. Z equals, that's why I do things before I make the videos. Negative 4, comma, 2 plus and minus 2 square root 3i. So it is based off of a radius of 4, but we still see some of those numbers taking effect. If you realize they generally do end up in a similar spot relative to 4. Square root 3 over 2 is to 1, as 2 square root 3 is to 4. It's multiplied. Another way to view it is if I multiply everything by 4, because the radius is now 4, that's where I get 2 square root 3. 2 square root 3. So it's the same relative position given a radius of 4. At this point, I should have just done it. It's the same relative position given a radius of 4. It's just that the radius is 4, but it's still the same situation. We just multiply everything by 4. It's stretched out, expanded by a factor of 4. So that's it for this De Mor's theorem. I'm going to run through quickly vectors. take a physics course or something. We're nearing the end. I think classes end this week, and then we're going to figure out what to do for the final exam. This is fun and interesting to discuss vectors in this context. Vectors are lines with direction and distance. They have a finite space. They don't just go on forever. And in which direction are they going? So I'm augmenting this. Let me share this screen. And I'm probably just going to go through it here. This will be posted, but if you want to go through and think about what's going on, the difference between distance and displacement: distance tells us how far we traveled. Displacement only tells us how far we are away from an initial point. The whole notion of, let's say we're in some sort of situation, some city grid. We've gone here, and then we made a left and we went here, versus going straight. This distance, displacement, where we're ending. Triangles abound, all that good stuff. So again, here's examples. Gravity pulls you down, all that, looking at wind trajectories and all that stuff. For those of you that are interested, I'm going to leave this just for your own benefits. I'm not testing this. This is fun and interesting, but we can definitely see connections here. Distance formula, Pythagorean theorem, equation of a circle using z. And even connecting this to magnitudes in the imaginary number plane, we would just find the distance here. And there's an easier way of doing this. You just take the absolute value of these values. Okay. So there you go. If you're curious and truly interested, go ahead and explore this if you want to. I'm just going to breeze past this. At this point, if we had more time, we would be going into 3 dimensions, but we don't have that time. There you go. And then lastly, definitely connect these to matrices. If we have any kind of complicated coordinate system, throw it into matrices, and we're back towards the beginning of the year with rotation matrices, rotating around a circle, and all that good stuff. And thus we've come full circle. Good job. Take care. There is no quiz posted. I will be posting a study guide, which is just all the quizzes I would have given with the solutions just for your own practice. Test Friday. And thank you.